11, we've been looking at the magnetic permeability, right? And we've seen the conductivity, electric conductivity. And electric conductivity is very useful parameter, and people use it very often in the geotechnical engineering to survey the field. And electrical conductivity, the reciprocal of the electrical conductivity is electrical resistivity, right? And it is function of the charge mobility, so how the charge can move freely, and that's correlated to the quantity of the charge, so how many charges you have in the media, and the velocity of the charge, so how fast they can move, right? So if you have an electrolyte, for example, salt solution, or the brine or seawater, then you have a high ionic concentration and you have many charges inside, so you have higher electric conductivity, right? In the low salinity water, the electrical conductivity will be lower than that. And I think we have derived some equation that can be applied for low ionic concentration in which the electrolyte electric conductivity is proportional to the quantity of the charge, so the concentration of the ions inside, right? And today we'll talk about the polarizability, and so that's correlated to the permittivity of the media, right? And the permittivity is a complex number, so we'll talk about that, and then that will be all for chapter 11. And polarization is very simple concept, so how the charge can move and polarize locally. So in this case, the material is dielectric. It's like oxygen or hydrogen or the water or maybe like plastic material, right? The dielectric material inside that they don't have free charge to conduct the current, electrical current, right? So when you apply the electric field, there is only a local movement of the electron or some ions inside, yeah? So this, then the polarizability, you can think of the spring and dash part too. So for example, so when we look at this is the hydrogen atom, right? So you have a proton inside the nucleus, and you have a electron cloud outside. Then when you apply the electric field, then this positive charge will move to the anode, right? And this one will be attracted to the positive charges, right? So this atom will be polarized, right? So then when you, if you remove this electric field, then this will go back to this original shape, right? So this can be, think of a spring model. So you have a spring, and when you apply the electric field, it's like applying the force. It deformed, and then if you remove the force, then it goes back to the original position or shape. So this is you can think of the spring, and then if you find the right frequency that can resonate, then it will make a resonant movement, right? So this electronic polarization shows the resonance type of behavior. And in this case, of course, there's a mass of the electron and the proton. So there will be a phase shift. So you need to use the complex number. But so we'll see the spectral response of this electronic polarization in the case of resonance. And so from here we are upgrading, upscaling it, right? So this is the atomic scale, and this is the molecule scale. And if you think of the ions or salt ion, maybe sodium chloride, then if you apply the electric field, then this will move, let's say this is the plus and minus, then this will move this direction and this direction, right? So it will stretch, and then if you remove the electric field, and it's gonna also again going back to the original position, right? So this also can be think of you can use the spring analogy, right? So then this will also show the resonance type of behavior, but in the different frequency. So here, for the electronic polarization, you have to go higher. The frequency should be around 10 to the 16 hertz. Okay? So this is a really high frequency, so that you can make the resonance of the electron cloud. But in the molecule scale, now the mass is increased, so that the resonant frequency will go down. So the resonant frequency range is 3 order of magnitude less than that, so 10 to the 13 hertz. So this is the ultraviolet area, UV, and this is the infrared area, so IR region. So have you heard of FTIR, the chemical analysis method? That method used this kind of a this frequency light. So you radiate this kind of a frequency light to the chemical and find out the resonance of the chemical material. So like CH bond will have a certain type of resonant frequency, and CO bond, the carbon and the oxygen bond, will have a different resonant frequency. And from there, you can find out what this material is made of. So FTIR is commonly used to find out the chemistry of the material, the pure material. So this also shows the resonant behavior. And if we go one more step, then molecule itself, on the top of their stretching it, molecule itself can rotate, right, and vibrate, and there could be a thermal agitation and the diffusion of vibration. So if the water molecule is here, and if you apply the electric field, then this will rotate this direction, the other direction, sorry, this direction, right? And when you remove this electric field, they will just also, they don't just go back to original position. It's not like springs, but they will randomly move and vibrate so that they can agitate, right? So this is not the spring, but their movement will be governed by the viscous drag around the media, right? Or the surrounding medium. So this shows their relaxation type of behavior. And the frequency will be much less than that. So this frequency is around 10 to the 9 hertz in the microwave frequency. So if we think about the resonant type of behavior, this is the frequency and the permittivity. Resonant type of behavior is you have very high peak at the resonant frequency region, and relaxation type of behavior shows this kind of a smooth degradation of the permittivity. So let's think about at the zero frequency. So now you are applying the static electric field to the molecule, and at that point you have a maximum polarization. So at the zero frequency, when the frequency is zero, your polarization of your media is the maximum. And once you start alternating the current, this polarization will go down because of the inertial force and the viscous drag. So here at the frequency 0, polarizability is the maximum. As the frequency goes to infinite, this goes to minimum value. And what is the minimum value of the permittivity, the relative permittivity? 뭘까? Electron cloud. So we've been looking at the electronic polarization. Here we are looking at the polarization of the electron cloud. Right? What's the smaller than that? So then it's just free space. Right? So when the frequency goes to infinite, then electron cannot follow that movement, the oscillation, because oscillation is too fast. So now you only have the permittivity of the free space. So the smallest one will be 1, because the relative permittivity of free space is 1. Right? That's the same with the dielectric constant. So A term, this is the electronic polarization, shows the resonance, and ionic polarization is for the molecular scale, and the orientation of the molecule shows the relaxation type of behavior at the microwave region. And when we draw the spectral response of real permittivity, kappa prime, and the imaginary permittivity, kappa double prime, and then you have these 3 distinctive regions according to the scale of the polarization. So at the low frequency, you have the maximum value. So I think this is the example of the water. So let's think about the water molecule. And water molecule have their permittivity value of 80 at the 0 frequency, and it's kept constant at some point when the orientational relaxation happens. Okay. So, and after this, when the frequency is larger than this relaxation frequency of the water, then the frequency is too fast, so the water cannot rotate, okay? So because of the inertia and the viscous drag. Then what can be polarized now? Water molecule itself can stretch, right? That's the ionic polarization, and that can happen in the IR region. Actually, in this region, you have 3 of these, right? Relaxation, orientational polarization, and ionic polarization, and electronic polarization at the low frequency region, right? So this is the electronic plus ionic plus orientational, right? And after this relaxation frequency, this will be cancelled because right now the frequency is too fast. And after this, the ionic resonance frequency, the frequency is too fast for the molecule to stretch. So you have only left with the the electronic polarization in this frequency. And when the frequency larger than this electronic the polarization frequency, the resonance frequency, then you have only relative permittivity of 1. That's for the free space. So now you are not polarizing anything in this frequency. Right? Question so far? So the microwave oven uses the frequency at around 2.4 gigahertz. That's around this range. Right? And the reason that microwave oven works is because they can rotate the water molecule and they can vibrate, and so then because that movement, it releases the heat, right? So that you can warm up the food. But so that's for the free water. But the frozen water will have the different, so ice in the water and the ice will have different orientational relaxation frequency, so that you have to use the different frequency to defrost the material. Right? So you have option for the noble food and the frozen food. Right? And frozen food, if you turn the knob to the frozen food, then the frequency the microwave oven emits is different. Okay? So I think that's part of the homework 4, right? So you can dig out more about that. So in the when the frequency meets at the relaxation frequency or the resonant frequency, you have a peak in damping. So here, for example, if I plot the damping, the loss, energy loss term for the resonance, you have very sharp peak like this. But the relaxation, you have wide peak like this. Okay? So here, you have peak bell-shaped curve with the center at the resonant frequency. Omega n, and here also you have resonant frequency at omega n. Here you have relaxation frequency that's omega r. And this is more like widely spread it like this. Good. This for the single material. So polarization can be expressed with this vectorial sum of the elementary dipole. So polarization is like if you have the material like this, and each dipole will have the dipole moment of mu d, and number of this dipole is the nd, so the small nd, and so and polarization P is the n sub d times the mu d, like this equation. And this dipole moment is proportional to the local electric field. So it's an external electric field. So this is the same with alpha time E local. So this is the symbol for proportional, linear proportional. So as we just saw it, there's a resonant type of behavior and a relaxation type of behavior. And resonant type of behavior can be expressed with this equation. Here the kappa prime and kappa prime naught is the permittivity at low frequency, almost at zero frequency. And the kappa prime infinite is the permittivity at very high frequency. Okay? And the R is the resonant frequency. And beta is like equivalent to viscous drag coefficient, like the C in the single zero frequency system. And it's a loss by radiation, so it's a loss term. In the relaxation type of behavior, we use the divide relaxation equation, and that's this one. And I think you are familiar with this equation because the shape is the same with the stiffness model here. So this is for the stiffness. So resonance is when the spring is dominant, and the relaxation is when the dash part is dominant. So the energy loss has the dominant term. And here we need to also think about the resonant frequency is what? So you can think of the swinging swing, right? And when you swing the swing, 말이 되나? 그네를 이렇게 하면 when you swing it, so if you apply the force at right time, the amplitude will increase, right? When you think about the pendulum, right? So that's the resonant frequency, right? And relaxation frequency is, if you think about the polarized molecule, the water molecule is polarized, and when you remove all the electric field, how long it takes to become randomly oriented. Like this is going to thermally agitated transition by diffusion. So that's the time for the relaxation time for relaxation. And the inverse of relaxation time is the relaxation frequency. So you can think of the door, the dash part in the door, right? And it takes time to go back to the closed position when you open it, right? And that's the relaxation time. Right? And when the dash part is dominant, this doesn't swing, right? It just goes smoothly to the closed position. Right? So that's why you have a smooth degradation in the real value. Right? So using these two equations, if you plot it against the frequency, then you get this frequency spectrum. So resonance, you have peak, okay? And the lowest term also you have a sharp bell-shaped curve, and the relaxation type of behavior, you have smooth degradation like this. Actually, we've seen this one in the Biot-Gassman equation, right? It's a little bit flipped. It's flipped. So there's in the Biot-Gassman, you have this kind of Vp naught and Vp infinite, right? So it's just because of the stiffness. But here you have decrease with the frequency. Right? So thinking about the single molecule. And this resonant type of behavior will be shown in the some bonding stretching and the ion cloud polarization. Then the relaxation behavior will be shown the orientational movement of the molecule itself. And relaxation of this spatial polarization is when you have two different material. So for example, you have sorry, this is A, and this is the material B. And when you apply the electric field, then this will have a certain polarization, and the material A will have the different polarization. Right? So that way that you have this, maybe one material is more polarized than the other material, so that you have this kind of a relaxation behavior. It's called a Maxwell-Wagner spatial polarization. And we'll talk about them more in the, I think, in a couple of slides. This is the review only. So, depending on the scale, the length scale or the time scale that you are looking at, this is the the electronic polarization, and the resonant frequency is around 10 to 16 Hertz, and this is ionic polarization, and this is orientational polarization. So ultraviolet, infrared, and the microwave. And I think it's the same. The electronic polarization, ionic polarization, also both shows the resonant type of behavior. And I think we've seen, so qualitatively I explained it. And the last one is the orientational polarization, which shows the relaxation type of behavior. I think this is important. Two equations, when you look at the top and the bottom equation, there's no temperature term. So the electronic polarization and the ionic polarization are not affected by the temperature significantly. But orientational polarization is what? This polarized water molecule will have to fight against the thermal agitation or random vibration, Brownian motion. So that's thermal agitation. If the temperature increases, then polarizability will decrease, right? Because the random movement will have the higher power. Right? So you have to overcome this thermal agitation to be polarized. So as the temperature increases, alpha decreases the polarizability. So temperature is an important factor in here. And here the tau is the relaxation time. So this is the reciprocal, the inverse of resonant frequency, or the relaxation frequency, sorry. And you can see that this relaxation time is proportional to viscosity of the media and the radius of the molecule, and inversely proportional to the temperature. Okay? So that means that if the media is more viscous and sticky, then it takes time. It takes more time to become going back to the original state. Okay? And also the radius. If the radius is bigger, then when you move, it takes more time, right? So I think it's very straightforward equation. Okay. Question so far? So we've seen the polarization of single material, single molecule, and now we'll see the effect in the soil media. So first we'll talk about the low specific surface inclusion, so therefore like sand. This is the case. Sorry, you have the water, and you have the soil, the sand particle, like this. And when you model, when you want to find out the effective permittivity of this mixture material, so you have two components inside, water and the sand particle, then you can make it to layered media, like this. This is the field, or parallel to it, or you can think of the inclusion. This is the layer. So you can idealize the mixture into two categories, layered media or the inclusion, the homogeneous media with some inclusion inside. So in case of layered media, if the layered media is parallel to the field, there is no relaxation. Right? So the water can be polarized freely, but only the difference is that you have smaller area is polarized. Right? That's gonna be proportional to the volume fraction of the water in the media. But in this case, the material is layered perpendicular to the electric field. Right? So then you have spatial polarization. So the water is highly polarized, but the sand particle, because it's dielectric and the crystal, is less polarized. Right? In this case, the Maxwell relaxation and you see that this spectrum can be applied. Huh? We'll see that in a minute. And host with inclusion is a spatial polarization and magma relaxation. This is the case you have an inclusion, So this is the homogeneous dielectric material, and you have the water. And what is this one? Clay. You have a clay material and the water, and this is an particle. Another example of the spatial polarization. This mixture, the polarization in the mixture is modeled with quasi-divide format, and it shows the relaxation response at radio frequency, and just divide type of relaxation formulation. On the top of that, you have this conduction part, conduction loss part. So this is a divide relaxation part, the same equation that we've seen, and this is the conductivity part. And if we don't have this part, then effective permittivity will be just like this. That's like bell-shaped curve. But because this equivalent conductive part, this is what? This part is inversely proportional to the frequency. So frequency increases, so the conduction loss part decreases, right? So that means that at the low frequency you have very high conduction loss. So you have imaginary component that decreases with the frequency like this. And if you combine these two, this is the pure imaginary permittivity, and if you combine this kappa double prime plus conduction loss part, then you have this, the black and dotted line. So you can see that the effective imaginary permittivity increases as the frequency decreases, because their conduction loss prevails. Okay. So when we think about the layered media, it's the same. When the interface is parallel to the field, this is the plus, minus. This is the material 1 and material 2. In that case, the mixture permittivity is still just the series, the parallel model. It follows the parallel model. And if it's normal to the field, the layer interface is normal to the field, and it follows the series model. And we derived this equation for the electrical conductivity in the last class, right? For the layered media. You can just replace the kappa with the sigma, then you have the effective conductivity for mixture. Okay, so there are many other mixture theory to calculate the property of the mixture when you know the volume fraction. So, for example, you have an inclusion inside, This is the inclusion, and this is the material 1. And you know the volume fraction, the volume of material 2, total is the D2, and volume of material 1 over total is the D1. And you know the permittivity of the D2, material 2, and permittivity of the material 1. And then what will be the mixture permittivity, which is function of D1, D2, kappa 1, kappa 2. Okay? So in this case, we've just seen that for the layered media series type model and parallel models there, right? And there are more like Maxwell model and Hansen and Strickman model, etc., etc. Okay? The same for the equivalent stiffness model. Okay, that's for the low specific surface soil. And what happens if you have, so in this, before we assume that the one inclusion is dielectric. It's not polarized. It's less polarized than the other one. But when you have a clay, water can be polarized, and also the clay material can be polarized. Right? So now two material can be polarized both. So then you have also spectrum of the frequency spectrum for the permittivity. And first one is the stern layer polarization. This is the clay particle, and at the stern layer, at the monolayer, you have a cation, and when you apply this electric field, this cation can move, but their movement is very locally bounded. But if the electric field is so strong and it's at the right frequency, they can jump from one well to the other well. Right? So because there will be a potential distribution according to the negative charge distribution. And this shows the resonance type of behavior. At low frequency, this does not contribute to the conduction. But at the high frequency, this charge can move, and this contributes to the polarization and the surface conduction. The second is absorbed water polarization. So you have cation at the stern layer, and also you have a absorbed water layer. That's very strongly binded at very surface. And this shows the relaxation type of behavior, because the water molecule itself has a mass and it has to rotate. So basically, if it's negatively charged, then water molecule will be polarized, oriented like this, right? So proton has the more positive pole, and the oxygen will have the more negatively charged. So the negative charged surface will orient and structure the water like this. But when you apply this electric field, very strong electric field, this can rotate, and it causes the absorbed water polarization. And the last one is double layer itself can deform. It's called a double layer polarization. And in this case, in the water molecule in the double layer, they are partially affected by the negative charge. And if you apply the external field, they will move. And this movement is not the spring movement. It will be affected by the dragging force by the surrounding other molecules. Right? So it shows the relaxation behavior. And the frequency is much lower than the other one. It's a kilohertz to the megahertz. That's for the one clay particle. And when you see the real permittivity and the imaginary permittivity according to the frequency, you have an electronic resonance, and here the kappa will be 0, right? And as the frequency decreases, now you are moving the water molecule that can stretch, or the salt, so that there you have an ionic polarization or stone layer polarization. And as you decrease the frequency more, now the absorbed water can move, and this shows the relaxation type of behavior. Relaxation. And this is around the pure water, and this is when the kilohertz, right? Kilohertz to megahertz. In this frequency range, you have another relaxation for the spatial double layer polarization, so that this part is by the contribution by double layer polarization. So in the sand, if you have a DI water in there, then polarization or the permittivity value cannot go above the 80 pure water value. Pure water value, let's say the pure water value is 80, then the maximum will be 80. And that's going to decrease according to the porosity. If you have a smaller porosity, then the permittivity value will decrease in the sand. But in the case of clay, this permittivity value can go above the 80 because you have a contribution by the clay particle. Okay? So this shows that the kappa prime can be higher than the 80. When you look at the loss term, effective permittivity, you have conduction loss part. So this is the kappa double prime imaginary part purely by the polarization loss. And you have another, so ignore this blue line, you have another bell-shaped curve. This should be originally like this for the relaxation, but because of the conduction loss, this increases with the decreasing frequency. Right? So conduction loss is this one. Conductivity over omega and epsilon naught. And if you look at the effective conductivity, so this is the AC conductivity. That's DC conductivity plus kappa double prime times omega times epsilon naught. In this case, you have a DC electrical conductivity, that's the lower bound, the minimum value. And as the frequency increases, because the polarization loss will be added, so that you have an increase in effective conductivity with frequency. Okay. So then spectral response of the clay. So here the polarization mechanism display one of two characteristic spectra. That's the resonance and the relaxation. In general, polarization mechanism that trigger restitution forces display a resonance spectrum. So restitution forces means that the force that tends to restore the energy. And you can see here for the clay, this kappa prime can be much larger than 80. So this will be the water value. This is the 80. And that's the kappa prime water. And for the because of the double layer polarization, this can go above the 80. And you have a absorbed water polarization and stun layer polarization, and there's a electronic polarization. And you can see that the conduction loss becomes prevailing and dominant when the frequency is less than, interesting, less than kilohertz, right? 10 to the 3. So GPR. Have you heard of the GPR? What's the frequency of GPR? Ground penetration radar. So you can have several type of antenna, and high frequency is around several gigahertz, and low frequency is like 20 megahertz. So that's around this range, right? And where is it? Megahertz is around this range, right? So GPR is, the frequency range is here, so that they can detect the permittivity of the water. Mostly it's affected by the water presence. And the TDR, time domain reflectometry, right? People use it to measure the moisture content. That's also around the gigahertz frequency. That's around here. Okay. And what is it? IP measurement or electrical resistivity measurement. That's around here. So that in that case, you have a conduction losses are dominant factor affecting the attenuation and the amplitude of the radar. So this is again another summary of the polarization of clay material. So high specific surface inclusion means that typically we can think of the clay, right? So the water itself can be polarized. On the top of that, in the high specific surface soil, you have also soil particle and the fluid interaction that can be reflected in the observed water polarization and stern layer polarization. Here, the stern layer polarization and bound water polarization shows that restrained movement of the bound ions and local movement of these ions due to their large energy barrier and similar to ionic polarization. And the second one is the bound water polarization. It's the same with the observed water polarization. And the third one is the double layer polarization. And when you have a DI water and clay particle, and you have only the deformation of the double layer, like this, and this is just the only local movement, right? But when it's in the electrolyte, the cation or the counter ion at the other end, one end can escape, and this can be replaced by the cation in the electrolyte to maintain the electro neutrality. Right? So, sorry. Yes. So in this case, the surface conduction occurs very actively. And the last one is the electrolyte. In the electrolyte, you have a high concentration of the particle. So the particle have a contact with the other particle. In that case, when you apply the field, so this is the electric field, then this counter ion can move, and that can be refused by the adjacent particle or from the electrolyte, so that the surface conductions are very active. I think it's the same. Okay. So far, any question? 질문 있니? 여기까지. 이게 단데 오늘? Okay. Okay, I think this is the summary. We can read it through. Let's read it through one by one. The first paragraph. Polarization involves charges with their own inertia. Because inertia force prevails in dynamic system at high frequency, a given polarization mechanism stops acting at high frequency higher than its characteristic frequency. So, what does it mean? So, when the frequency is larger than some resonant frequency or relaxation frequency, that mechanism just dies because they don't move. It's like a water molecule itself is too big for high frequency in that case, right? At some point. Polarization from different mechanism accumulates towards the low frequency. As a result, real permittivity increases with decreasing frequency. So you can see that at the high frequency and as you go low frequency, you have a electron cloud polarization and ionic polarization and molecule orientation, and there's a double layer polarization, right? And at this point, this is the low frequency, and you have all the polarization together. So that's why you have the highest polarization value at the DC, at the zero frequency. And as the excitation frequency approaches the critical frequency, like relaxation and resonance, polarization of the media lags behind the applied field. This phase lag manifests in losses and is captured in the kappa double prime, so imaginary value. So that means that for example, at relaxation frequency, because that time scale is perfect for that system, so that you have energy loss very high, so that they just move smoothly, degrades. And effective imaginary permittivity includes polarization losses and the conduction losses. I think we've seen this one. And we can capture only this effective term because they are in the same phase. Contribution of ohmic conduction to the effective imaginary permittivity. So kappa double prime decreases with the increasing frequency. It's the same. I think we can see from the previous equation. And at sufficiently low excitation frequency, ohmic loss takes place. Polarization is at its maximum, and the spatial distribution of charges is stable in time. As the excitation frequency increases, approaches the characteristic frequency, the real permittivity begins to decrease because the charges do not have enough time to reach the maximum polarization position. On the other hand, local displacement of charges become unrestricted, and the charge displacement begins contributing to the effective conductivity. So the effective conductivity increases with the frequency across the relaxation polarizations. Good. The last slide shows the characteristic of the internal scale comparing to the time scale. So here, for the single phase material, you have molecular orientation relaxation, ionic resonance, and the electron resonance. That's what molecular orientation relaxation is 10 to the 9, so that's about gigahertz. This is terahertz, 10 to the 12, and 10 to the 15. So this is the UV region and the IR region. This is the microwave region, right? And for the mixture, now you have another relaxation behavior at the interface. When you have a sand particle, you have a Maxwell or the Wagner relaxation. And when you have a clay particle, you have a double layer relaxation. So that's below the 10 to the gigahertz, 10 to the 9 hertz. So, and this. The velocity of the light or the velocity of the electromagnetic wave is lambda times frequency, or the light of speed over the square of the kappa prime. Right? Then from that, the lambda is c naught over f times the square root of kappa prime. So let's compare this lambda with the particle size. Because when the particle size is similar to the wavelength, the wave can scatter, right? So to be equivalent, you have a particle size like this. We've seen it from the Brillouin effect. If the wavelength is this much, then it can scatter, right, and reflect. But if the wavelength is like this big, then you can penetrate the media as convoluting the material property. So let's calculate this value when the particle diameter is 1 centimeter and the kappa prime is 80. What's this value? C naught is, how much is it? The light of speed, 3 times 10 to the 8 meter per square over D is 10 to the negative 2 meter times kappa prime is root 2 80. So this is, let's say that this is 81, then this becomes 9, right? 9. So one, 3, thing. How much is it? This is 0.33. So 3.3 times 10 to the 9 hertz. So when the frequency, when the particle size is like about 1 centimeter, then this value is around 3 gigapascal. 3 gigahertz. So frequency should be much lower than that. So when the particle size is 1 centimeter. So the antenna or the GPR, if you want to use the GPR to avoid the reflection or the scattering by the particle, then to have the more penetration depth, the frequency should be less than that. So if it's larger than that, then you have energy loss by the scattering or the reflection. So always, when you choose the frequency range, what's the internal scale of your media and what's the penetration depth that you want to know is the key point. That's a very important factor to consider.